you guys. I hope you're doing well and staying safe and staying healthy. It's day 10 of our current predicament. I hope you're inside practicing social distancing. If you must go outside, we can do this. We can flatten the curve, but it's going to require effort on the part of everyone, especially you guys. So share what you know with your family and your friends, and definitely stay safe and stay in if you are possibly able to do so. We'll continue on with vision and talk about receptive fields. So this one in particular, I wish we were in the lecture hall for, because it tends to be one of the more elusive concepts in the course, but we're going to go over it, and then we're going to go over it, and then we're going to go over it again. And hopefully if I take my time and you take your time reviewing, then receptive fields should certainly be something you can conquer, and you'll work on them again in next week's tutorial activity. So I'd like to point out one of my favorite artists. Georges Seurat was a French post-impressionist that utilized and arguably developed the technique of pointillism. And one thing you can see in Seurat's work, particularly his monochrome or black and white works, is the way he used pointillism to highlight or accentuate the borders between dark and light, borders and edges where dark meets light. So if there's one takeaway from this lecture that you should write down right now, it's borders and edges where dark meets light. That is the entire function of receptive fields, or it's a good summary of the function of receptive fields within the retina. So let's get going. This is Woman Seated by an Easel by Georges Seurat. Your textbook is minimal on this stuff. Use the detail that I've included in the slides. I'm gonna post some sensory physiology files. Those will be called the Dr. Tudis files on Canvas. They have really good supplementary information, so you utilize that perhaps as opposed to your textbook in this case. We'll start off with lateral inhibition, which we've talked about throughout the course and is certainly relevant here. We'll talk about two different types of bipolar cells, on bipolar cells and off bipolar cells. Throughout the course, I've tried to stress the idea that it's not about the neurotransmitter, it's about the receptor. The response that is elicited in a target cell is related to the type of receptor that is present rather than being a function of the specific neurotransmitter that's released. We'll build up and talk about center surround systems and why it's useful in terms of vision. And I'll tell you that right now. It's useful in terms of vision for accentuating borders and edges where dark meets light. Okay, so the basic principle of lateral inhibition. So here the specific diagram is showing a stimulus, a touch or a pinprick of some kind in skin, and there will be a primary neuron that is maximally activated, and then other neurons over here in orange that are activated to a degree. But in any case with lateral inhibition, the neuron that is activated most strongly will send inhibitory collaterals to neighboring neurons to turn them down. So the scenario shown up here in A1 is in the absence of lateral inhibition. So you have a central neuron in red that's activated to a greater degree, and then you have two slightly more peripheral neurons that are activated to some degree. And then if you were to think about the perception of where that specific stimulus is, hopefully you can imagine that in the absence of lateral inhibition, it will be relatively diffuse. Whereas in the presence of lateral inhibition, and I don't want you to worry about drawing this out. I would never ask you to draw this particular circuitry. I just want you to take away the key point, which is this central neuron in red that is maximally activated has inhibitory collaterals that synapse onto neighboring neurons. So those neighboring neurons will be inhibited. So only the neuron that fires to the greatest degree is going to activate its secondary neuron. And so you'll get firing in the secondary neuron, the red one, but not in neighboring neurons. So lateral inhibition inhibiting my neighbors, right? So that only the neuron that is activated to the greatest degree is firing. So lateral inhibition we could find in any of the sensory systems we've discussed so far in the course. It's perhaps easiest to understand in the context of skin and localization of a stimulus, but we've talked about it along the cochlea. It's certainly relevant in all sensory systems and certainly relevant in the retina. So the takeaway from this slide is not the circuitry. The takeaway is the principle of lateral inhibition. One neuron that is maximally activated will inhibit its neighbors, and that will increase the precision with which a stimulus can be identified, whether it's location or otherwise. And in the case of vision, lateral inhibition is important for high acuity color vision. Okay, so we can look at these Mach bonds named for Ernst Mach, who was a German physicist who described them a number of decades ago or centuries ago. If you were to look at this region, so I'm looking at the second band, the second gray band, and if we were in lecture, I would ask you to tell me which side of this band is darker and which side is lighter. And hopefully you would agree with me that we all perceive this side of the band to be lighter and this side of the band to be darker. If we move to the third band, the same is true. I hope you'll agree we perceive that this side of the band is lighter and this side of the band is darker, and so on and so on. If we move over here, this is lighter, this is darker. I hope you'll agree that that is our perception. However, if we were to plot the perceived luminescence, that is true. We perceive that it is darker on lighter on one side and darker on the other, or vice versa, right? Lighter here and darker here. So our perceived luminescence does not match the actual luminescence. In actuality, despite what you perceive, the luminescence of this band is the same here as it is over here. And I know you don't perceive that. However, the luminescence of the Mach bonds, if you were to cut these out, print this slide out, print this out on an 8x10 piece of paper and cut these along the lines between them, and you'll see that when they're not juxtaposed next to one another, they are absolutely equal in luminescence from one side to another. Okay, so the actual luminescence differs from our perceived luminescence. So this is an optical illusion, but it is driven by, or it results from, differential activation of receptive fields in the retina, which is our entire topic for today. All right, so last time when we talked about molecular physiology of vision, we talked about photoreceptors. So here we're looking at the cones. Cones are photoreceptors. So cones, like rods, and I stressed this last time, so if you need to go back and revisit, please go back and revisit. You should all be able to tell me that photoreceptors in the dark are depolarized and they're spitting out glutamate onto neighboring bipolar cells. In response to photon or photons of light, cones will hyperpolarize, resulting in decreased release of, you should recall the neurotransmitter is glutamate, and you need to know that signal transduction pathway. I won't review it for you here. That was covered last lecture. And then there's two different types of bipolar cells. There's on bipolar cells and there's off bipolar cells. And I'll post a short paper on that for you as an additional source of information. But on bipolar cells, so we're following the right here pathway. And an on bipolar cell has glutamate receptors that are GPCRs. And you should recall that GPCRs are metabotropic receptors. So an on bipolar cell has metabotropic glutamate receptors. And in the dark, remember what's happening in the dark. And my approach to this, all visual signal transduction pathways is start in the dark. Tell me what's happening in the dark and then move to what's happening in the light. So in the dark, remember, photoreceptors are depolarized in the dark and releasing neurotransmitter. So in the dark, glutamate release from the photoreceptors and mGlu-R activation keeps a channel. Remember, we talked about different things that GPCRs can do, and downstream of GPCR activation in many cases is inhibition or activation of ion channels. So when glutamate levels are high in the dark and mGlu-R activity is high in the dark, downstream of mGlu-R activity is TRPM1 channels. And mGlu-R, the alpha subunit of mGlu-R, inhibits yet another TRP channel called TRPM1. So in the dark, metabotropic glutamate receptors are active, and TRPM1 channels are therefore inhibited. TRPM1 channels are closed, meaning there is no depolarizing current through those TRPM1 channels, and therefore on bipolar cells are hyperpolarized in the dark. On bipolar cells are hyperpolarized in the dark. Now, think about what happens when there's light. When there is light, photoreceptor cells will hyperpolarize. There'll be a decrease in glutamate release and a decrease in mGlu-R activity. If you decrease mGlu-R activity, you're going to open your TRPM1 channels. Open your TRPM1 channels, remember they're non-selective, sodium in, calcium in, depolarizing currents that will depolarize the bipolar cell in the light. Depolarized bipolar cells will release glutamate onto the retinal ganglion cells, which are the neurons in this pathway that will produce action potentials. Okay, so mGlu-Rs then are inhibitory because when you have high levels of glutamate release in the dark, high levels of mGlu-R activity, your on bipolar cells are hyperpolarized. They're not excited. Okay, so on bipolar cells are turned on. They're excited by the light. Okay, excitation of on bipolar cells in the light due to decreased glutamate release by their partner photoreceptor cells, decreased glutamate release, decreased mGlu-R activity, increased current through TRPM1 channels, depolarization, and in the light, an increase in glutamate release by the on bipolar cell onto the ganglion cell. Okay? On bipolar cells are excited by, are turned on by the light, and they result in an increase in retinal ganglion cell firing. You might need to rewind me and listen to that again, but we're going to go over it. We're going to go over it. We're going to go over it again. So hopefully by the end of the lecture, you will be very clear on the difference between an on bipolar cell and an off bipolar cell. So for an off bipolar cell, now we're looking at the left side of this diagram, and the story starts the same way. Cones, rods, photoreceptors always are depolarized in the dark and always hyperpolarized in response to light, resulting in a decrease in glutamate release. Unlike on bipolar cells, which we just said have metabotropic glutamate receptors, off bipolar cells have ionotropic glutamate receptors, or IGLURs. On bipolar cells have mGlu-Rs. Off bipolar cells have IGluRs. And IGluRs are ion channels, and their activation will depolarize an off bipolar cell. So in the dark, photoreceptors are depolarized. In the dark, photoreceptors are spitting out glutamate. Glutamate binds to ionotropic glutamate receptors, IGluRs, opening them, resulting in a depolarizing current in the dark. In the light, photoreceptors hyperpolarize, decrease glutamate release, decrease IGluR activity, and off bipolar cells in the light will hyperpolarize and reduce glutamate release, which will reduce firing rate in their partner retinal ganglion cell. Okay, so hyperpolarization of off bipolar cells in the light inhibits the firing of action potentials in the retinal ganglion cell. So off bipolar cells express IGluRs, and they're turned off by the light. On bipolar cells are excited by, turned on by the light. Off bipolar cells are inhibited. They're turned off by the light, which results in a decrease in retinal ganglion cell firing. If you need to go back and listen to that again, do so that you're clear on the difference between an on bipolar cell, which is turned on by the light, and an off bipolar cell, which is turned off by the light. On bipolar cells have mGluRs that are inhibitory. Off bipolar cells have IGluRs, which are excitatory. Okay, so if you're okay with on bipolar cells and off bipolar cells, then let's move on to center surround receptive fields. Before I do that, I'm going back a slide because once again, your textbook is illustrating this as if a photoreceptor can synapse onto both an on bipolar and an off bipolar. And hopefully you'll agree with me that if that was the case, if you were to shine light on this photoreceptor, you would equally excite it and equally inhibit it. There would be no net change. So the circuitry here can be very complex, but for our purposes, there will be either an on bipolar cell or an off bipolar cell, but not both. Okay, so the circuitry that we'll talk about will include photoreceptors and off bipolar cells, or photoreceptors and on bipolar cells, but not both at the same time. Okay, and I'll keep repeating that statement as we work through this circuitry. So you would correctly refer to the receptive field of a ganglion cell. A ganglion cell has an area of the retina, a region of the retina that it is sensitive to. And receptive fields are arranged into center surround systems. So there will be a center, you can think of it as concentric rings. There will be a center and there will be a surround. Here the center is shown in yellow and the surround is shown in red. And there's two different types of center surround organization that are important for us. One is an on center, off surround, and the other is an off center, on surround. And those names are not too complicated. They tell you pretty much exactly what's going on. In an on center system, you will excite the ganglion cell if you shine light in the center. And you will inhibit the firing of the ganglion cell if you shine light on the surround. It is therefore an on center, off surround. And the other arrangement is an off center, on surround, where if you were to shine light on the center, you will decrease the firing in the retinal ganglion cell, and if you shine light on the surround, you will increase it. So as we saw in the previous slide, light always hyperpolarizes photoreceptors. That is always true, but the photoreceptor can hyperpolarize or depolarize the bipolar cell depending on whether or not it's an on bipolar or an off bipolar cell, depending on whether it has M gluars or I gluars. So that depends on what type of bipolar cell is at the center of the system. Key point, for our purposes, whether it is an on-center system or an off-center system depends on the type of bipolar cell found at the center. If there's an on bipolar cell at the center, then we have an on-center system. If there is an off bipolar cell at the center, then we have an off-center system. Okay. Summarized down at the bottom. An on-center off surround, if you shine light on the center, you will excite the ganglion cell. If you shine light on the surround, you will inhibit the ganglion cell. And an off-center on surround, if you shine light on the center, you inhibit. If you shine light on the surround, you will excite. Okay. And whether it's an on-center, off-surround, or off-center on surround is determined by the type of bipolar cell that's found at the center. We're going to zoom in on the circuitry, and that will hopefully become clear or clearer on the coming slides. All right, so let's think through the circuitry. If we're going to build a center surround system, we need a center and we need a surround. And so again, this diagram is summarizing both possible pathways, but any given center surround system will be either an on-center system or an off-center system. It won't be both at the same time. So if you have the PDF of these slides in front of you or beside you, just draw a dotted line down the center so you know that one scenario is being depicted on the left and the other scenario is being depicted on the right. So let's think about what's happening on the left first, where we have an on-center, off-surround. If we were in lecture, I would ask you, if it's an on-center, off-surround system, then shining light on the center will do what to the cone? And you would hopefully tell me that shining light on the center will, as always, hyperpolarize the cone, decreasing glutamate release. And then remember, your on-center bipolar cell has M gluars. So if you decrease glutamate release, you're going to decrease M gluar activity, which is going to result in an opening of TRPM1 channels. The on bipolar cell will depolarize. Releasing neurotransmitter and causing firing in the ganglion cell. So an on-center system shown on the left, and we're just talking about the center right now. We'll talk about the surround in a minute. An on-center system is turned on when you shine light on the center. You hyperpolarize the cone, you decrease neurotransmitter release, you decrease M gluar activity, you open TRPM1 channels, bipolar cell depolarizes, increases glutamate release onto the ganglion cell, and increases firing in the ganglion cell. And this figure I've taken from the TUDIS supplementary material. It's quite good in its descriptions of what's going on here, so do reference that if you need an alternate explanation. On the right, we're looking at the center. We'll talk about the surround in a minute, but we're looking at what happens when you shine light on the center of an off-center on-surround system. Remember, your off bipolar cells express I gluars, ionotropic glutamate receptors, and shining light on the center, as always, will hyperpolarize the cone, which will decrease neurotransmitter release. Decrease in glutamate will lead to closure or closing of ligand-gated ionotropic glutamate receptors. And if you close ionotropic glutamate receptors, that will result in an absence of an otherwise depolarizing current, which will lead to hyperpolarization of off bipolar cells in the light, reducing neurotransmitter release, and decreasing action potential firing by the only cell in this system that produces action potentials, which is the ganglion cell, okay, RGC or retinal ganglion cell. So an off-center on-surround system is turned off when you shine light on the center. And again, covered very well in the Tudis supplementary material. All right, so if you're comfortable with the center and what's happening in the center, let's move on to the surround. If you're not comfortable with the center, go back and listen again until you are comfortable with the center. So let's think about the surround. Same information, just shown slightly different depictions of the circuitry. So let's just review the center first. Here we're shining light on the center. You should be able to tell me that that will hyperpolarize. You're seeing a hyperpolarization here that will hyperpolarize the cone. That will reduce glutamate release by the cone or photoreceptor. And that will reduce the activity of mGlu-Rs. And you know that downstream of mGlu-Rs are TRPM1, so that will relieve the inhibition on TRPM1, leading to depolarization, shown here. Depolarization will increase glutamate release and increase firing in our retinal ganglion cell. Okay, so we've just revisited what's happening in the center. Don't worry about the lateral geniculate nucleus. We'll get to that later, but this is the thalamus. The LGN is a region of the thalamus, and the SC is the striate cortex or visual cortex in the occipital lobe. We'll build up to that. The surround involves lateral inhibition and inhibitory interneurons. Last time we mentioned the horizontal cells, and we said the horizontal cells are important, and here they are, being important. So if we're going to build up the surround of a center surround system, we don't need any more bipolar cells. Okay, the bipolar cells are at the center, at least for our purposes. The surround is made up of cones. So we have cones and we have horizontal cells. So surround is made up of cones that synapse onto horizontal cells, interneurons, that synapse onto the central cones. And so this is an on-center, off surround. We know that because we have on bipolar cells at the center expressing mGlu-Rs. The surround, we don't need any more bipolar cells. We just need a bunch of cones. There's only one shown here. But we'd have a bunch of cones going around the periphery. And those cones synapse via horizontal cells onto the central cones. Okay, so if we were to shine light on the surround, cone cells here, these are excitatory. Cones, as cones do, release glutamate. Horizontal cells are GABAergic. Okay, they release GABA and they inhibit central cones. So if you were to shine light on the surround, as always, you will hyperpolarize your photoreceptor. If you hyperpolarize your photoreceptor, you will reduce excitation of your horizontal cell. And if you reduce excitation of your horizontal cell, it will no longer be inhibiting your central cone. If you're not inhibiting your central cone here is in the dark. We're not shining light on the center, we're shining light on the surround. So you can imagine your central cone being in the dark and doing what cones do in the dark. In the dark, photoreceptors are depolarized. They'll be releasing glutamate onto the bipolar cell, And releasing glutamate onto the bipolar cell will increase mGluR activity, and that will lead to closure of TRPM1, and that will lead to hyperpolarization of your bipolar cell, which will lead to a decrease in firing in your ganglion cell. So in our on-center, off-surround system, when we shine light onto the surround, we turn the system off. And that's mediated through lateral inhibition via the horizontal cells, which are GABAergic. Okay, so when you shine light on the surround, you decrease glutamate release onto the horizontal cells. Horizontal cells stop inhibiting the center photoreceptor. So your central cone here becomes disinhibited, and that results in increased mGluR activity, decreased TRPM1 activity, hyperpolarization, and a reduction in firing rate in the ganglion cell. So key point, an on-center, off-surround system is turned off when you shine light on the surround and turned on when you shine light on the center. So if you're ever asked to draw out this circuitry, which you will be at some point, you can use depictions like this. So I've just created these in PowerPoint and used triangles and circles and denoted synapses. So I would expect you to be able to draw out something similar. So the next few slides will review what's happening in an on-center system and an off-center system in the dark and in the light. I always encourage you to start in the dark and then move to the light. So in the dark, well, everything will be, what will be true of all of these photoreceptors in the dark? In the dark, photoreceptors are depolarized. They'll be releasing glutamate. So you'll have your central cone will be, it's depolarized, so it'll be releasing some amount of glutamate, but also remember your surround cones are also depolarized in the dark, and they'll be releasing glutamate onto the inhibitory GABAergic horizontal cells. And the horizontal cells, in turn, will be releasing GABA onto the central cone. So there'll be a little bit of excitation and a little bit of inhibition and some amount of glutamate that's released from the central cone onto the bipolar cell. This is an on-center system, so we have mGluRs. If we have glutamate release and mGluR activity and closure of TRPM1 channels, these are going to be largely hyperpolarized. So it's not that there will be no firing rate, but you'll have some baseline level of firing that we can then turn up or we can turn down. So in the dark, the basal firing rate will be determined by the partial excitation of this central photoreceptor as well as its inhibition through the excitation of the surround photoreceptors. Basal firing that we can then turn up or turn down. In the light, now we're shining light on the center of our on-center system. If we shine light on the center of an on-center system, we're going to hyperpolarize our central photoreceptors, decrease in glutamate release. Decrease in glutamate release means a decrease in mGluR activity, activation or opening of TRPM1 channels, depolarization of our on-bipolar cell. Depolarization of our on-bipolar cell will lead to an increase in glutamate release, and compared to the basal firing rate, more firing in our ganglion cell. On the next slide, let's look at shining light on the surround. We shine light on the surround of our on-center, off-surround. You should be able to predict what's going to happen if it's an on-center, off-surround. We're going to hyperpolarize our photoreceptors in response to light. That'll decrease glutamate release. Decreasing excitation of our horizontal cells means a reduction in GABA release from our central cone. So we can think of our central cone as being disinhibited. It will go ahead and do what cones do in the dark, or photoreceptors do in the dark, and spit out glutamate. You spit out glutamate onto an on-bipolar cell containing mGluRs. increased mGlu-R activity, decreased TRPM1 activity, and hyperpolarization. Decreased glutamate release from the on-bipolar cell onto the ganglion cell, and less firing in our ganglion cell. Okay, so make sure you're clear for an on-center, off-surround system, what's happening in the dark, what's happening when you shine light on the center, and what's happening when you shine light on the surround. We can do the same exercise moving over to the right side of the slide, looking at an off-center on surround. You know that it's an off-center system because at the center you have an off bipolar cell expressing IGLU-Rs. And in the dark we have the same situation. You have center cones that are partially excited, and then you have some inhibition by the peripheral cones, which are also excited and exciting the inhibitory horizontal cells. So you'll have a basal firing rate that reflects a balance between partial excitation and partial inhibition. If we shine light on the center of an on-center system, our cone or photoreceptor will depolarize. It will hyperpolarize. Okay. If we shine light on the center of an off-center system, the photoreceptors at the center will hyperpolarize. Photoreceptors always hyperpolarize in response to light. If we hyperpolarize our central photoreceptors, that's going to result in a decrease in glutamate release. A decrease in glutamate release onto off-bipolar cells that express ligand-gated IGLU-Rs is going to lead to closure of IGLU-Rs and hyperpolarization of our off-bipolar cell. Less glutamate onto our ganglion cell and less firing by our ganglion cell. So we shine light on the center of an off-center system, we end up with a lower rate of firing in our ganglion cell as a result. Now let's shine light on the surround of our off-center on-surround system. As always, we're going to hyperpolarize our photoreceptor, decrease in glutamate release as a result of hyperpolarization, decreased excitation of the horizontal cell, and a decrease in GABA release by the horizontal cell. There's a decrease in GABA release by the horizontal cell. This cone, which is effectively in the dark, right? We're shining light on the surround, not the center. This cone will go ahead and do what cones do. In the dark, they're depolarized. They are releasing glutamate, in this case, onto off-bipolar cells expressing IGLU-Rs. So increased glutamate will be increased IGLU-R activity, which will depolarize the off-bipolar cell, resulting in more glutamate release by the bipolar cell onto the ganglion cell and an increase in firing. So shining light on the surround of shining light onto the surround of an off-center on surround results in increased firing in the ganglion cells. Okay, so summary, I won't read through these bullet points for you. I hope I've repeated them or paraphrased them multiple times, so I'll let you read through them and make sure you're clear on each, and if not, go back and look at the on-center off-surround and off-center on-surround circuitry as much as you need to, so that you're clear on these key summary bullet takeaway points. This is not something I just want you to memorize. Of course, some memorization will be involved, but if you can think through the circuitry and think through the receptors, mGlu-Rs versus IGLU-Rs, this will make much more sense than if you simply go for just rote memorization. So make sure you're clear, you can discuss, you can explain, not just draw the circuitry. I'll be asking you to explain what's happening, not just draw it out. Okay, so a couple of key, this should be summary by now. We've got on-center illumination. So if we have an on-center off-surround system and we're shining light on the center, the yellow bar over here represents our light. We've got some baseline or basal firing rate, and we increase it when we shine light on the center. Don't worry about the slow return to basal over here. There's recovery. There's photo bleaching that happens. I touched on that briefly last lecture, and it's beyond our scope, so we don't need to worry about it here. But suffice to say, when there is light being shined on the center, we have an increase in the firing rate of the retinal ganglion cell, right? Remember, when you're talking about receptive fields, you're talking about the receptive fields of a retinal ganglion cell. Okay, when you shine light on the center of an off-center system, you reduce the rate of firing in the retinal ganglion cell. So you have some baseline level of firing. In the presence of light, you have a decrease in the rate of firing, and then a return to baseline again. And don't worry about the more rapid rate of firing over here compared to over here. That again is beyond our scope. Key information is here. In the presence of light, there's a decrease in the rate of firing. Okay, all of that is summarized here. I'll let you look through this one on your own and maybe predict the difference in firing if you have an on-center versus an off-center system, respectively. So let's come all the way back full circle to our Mach bands. Why Mach bands? Why is it that we perceive that this side of the band is lighter and this side of the band is darker, when in fact the luminescence is equal through the entire width? And it has to do with the differential activation of receptive fields that lie at the boundary between darker and lighter, or here, darker and lighter, borders and edges where dark meets light. So these guys that are sitting in the middle of a Mach band are kind of, we can think of them as sleeping, because regardless of whether they're an on-center or an off-center system, they will be equally excited and equally inhibited. So we can think of those guys as sleeping. However, the ones that are at the border, where they have part of their center surround system in one area of luminescence and part of their center surround system in another band of luminescence, those are giving more information. So this one will be saying lighter, this one will be saying darker, and so the boundary between the two is accentuated, okay? Because the ones that are in the middle are sleeping. They're equally excited and equally inhibited. The receptive fields that are at the boundary, at the border where darker meets lighter, are giving you more information. And therefore you perceive this region as darker and this region as lighter, as compared to the regions that are halfway through the bands. Okay, so key point, borders and edges where dark meets light. And again, if you want to read through this, the Tudis material is very good, but the key point is here at the bottom. The receptive field over the dark band, this guy here, is receiving more surround inhibition because part of the surround is in this brighter area. So the excitatory response is less, and that results in a perception that this area is in fact darker than it actually is. So I would never ask you to tell me, is this on center or off surround, and is this one on center or off surround, and why. We're not going to go there. You need to be able to explain the circuitry of an on center system and an off center system, and you need to be able to explain why the receptive fields that are found at the border matter more, because they're giving you more information than their counterparts that are effectively sleeping. But that's the point. So this is accentuating borders and edges where dark meets light. All right, well now you hopefully have something interesting to tell your friends and family, perhaps over Skype or a virtual happy hour, or however it is you're interacting with people these days. Stay well and stay safe, and we'll pick things up, a few review questions for you to look through, and we'll pick things up on Wednesday. I will talk to you then. Stay well, stay safe.